Hello, everybody. This is our second topic in our chapter 2 relating to research. We talked about descriptive methods already, so now we're moving into correlational designs. In correlational designs, we're looking at relationships between and among variables. And I think that this little icon might be blocking my screen, but if you can see the little joke, the joke is showing a Venn diagram with some points in it that says, I can see everybody who went to the moon has eaten chicken. And they noticed a relationship between chicken eating and going to the moon. And it made the other guy say, good grief, chicken makes you go to the moon. And that's a classic fallacy of a correlational design. So let's move forward and take a look at what these are and why they're false. Why that's a false conclusion. So we'll talk about correlations, scatter plots, Pearson R values, and 3 important reasons correlation does not equal causation. Beginning this topic, let's talk about variables. A variable is a factor of what we're primarily interested in when we study psychology. These are factors that vary among individuals, or they are different among individuals. So things that we can measure that differ among us. So for example, we have different eye color, we have different names, we have different cars, we have different heights, we have different weights. We make a different number of posts on our social apps. We have a different number of siblings, a family member, of friends, of pets. We might be feeling in a different emotional state right now. We might be having different levels of interest in something right now. All of these are examples of variables. Variables come in different types. Nominal variables are categories that differ by name, but all are equal. So some examples of these might be some of the first that I gave you now. We all have different types of cars. If we have a car, we have different eye color. We have different animals, different pets, so they're categories. If we take any of those that I just gave, let's say types of pets you have owned in your lifetime would be a nominal variable. So maybe you've owned cats, dogs, mice, horses. Say those are the pets that you've owned, the types of animals that you've owned as pets. So it wouldn't matter if I was making a chart showing what pets each of us has owned. It wouldn't matter what order I put the bars in. I could put horses first, I could put cats first. It wouldn't make any difference. But if we have ordinal variables, the order of the categories is important. So we might have the same kind of graph, we might have categories with names, but the order would be important. And for example, I would say that if we polled a bunch of people on income and we had them we gave some parameters and said, do you fit into the low, the medium, or the high income group? We have categories, but we would put the medium in the middle and high and low on the ends. The order would make a difference. It wouldn't make sense otherwise. So that's the difference between nominal and ordinal variables. The variables we're most interested in here, let me just go back and address the second example I put on my screen. High school grade, freshman, sophomore, junior, senior. Let's say I was interested in how many freshmen, sophomores, juniors, and seniors there were, and I was going to make a frequency chart or a bar graph that's showing how many freshmen, how many sophomores, how many juniors, how many seniors. It would be silly to mix up the order. I would want to put freshmen first, then sophomores, then juniors, then seniors. So again, an example of an ordinal variable. The variable of interest for us today are these continuous variables. They're not categories at all, but they're numbers that could fall at any place along a scale. And since they're relevant for correlations, let's take another look. My examples here, let me move this little icon again. My examples here are height. Of course, it varies, and we could fall anywhere. You know, I am about 5'4.5" and maybe you're 5'7" and maybe someone else is 6 feet 2 inches. We could fall anywhere along a scale. The scale would have ends, but within those ends or ranges, within that range, we could fall anywhere. I also put, and you can't see because of this icon, but I also put the number of credit hours would probably range from 1 to maybe the maximum we would have would be 21, and you could fall anywhere along that continuum. And I think I might have put looks like I have hours or something down there, and I'm not able to move this right now. So let's continue on. So here are our nominal variables. There's an example of this bar chart that I gave you, and we're just looking at favorite colors. And this is a graph maybe from a school teacher who asked her class her favorite colors. And you could see that yellow was the most important, but it wouldn't make any difference if we put yellow over here. The names are important, but not the order. That's compared to this second histogram, which is showing the ages of participants, and 0 to 10 is here, 11 to 20 is here, 21 to 30, 31 to 40, and so forth. It would be silly if I took this 41 to 50 bar and put it way over on the end. We want to keep these in order, so they're ordinal variables. And our continuous variables look like this. You want to have a number line, perhaps between the ages of 21 and 40. Maybe I would ask the ages of people participating in professional sports. And let's say at the lower end was 21 and at the upper end was 40, and people fell anywhere along this continuum. These continuous variables are what we use in correlational studies. And there are other examples here: minutes to school, number of Facebook friends, hours of sleep per night, level of happiness from 1 to 10, and so forth. So for this little example, if I was live with you, I would ask you to consider the answer to the following question. Consider that overall happiness is one variable, and let's make it a continuous variable rated on a scale from 1 to 10, and let's assume we have a good way to measure it. Okay? What other variable might relate to it? In other words, what other variable might tend to be higher in people who report higher levels of happiness? So that's the question that I would ask you to answer in a group. Other student groups have suggested things like these. Since I don't have you in front of me, they've had things like the number of close relationship, the amount of sleep you get a night. The more sleep you get each night, maybe the happier you are, you know. Hours of work. Maybe they're hypothesizing that fewer hours of work might contribute to greater happiness. These are just ideas proposed by students. Maybe the number of friends you have. And people have proposed money. The more money you have, the happier you are. So these are some ideas that we might, if we were interested, we might be wanting to examine to see if there is in fact a relationship. So keep that in mind, whatever you think might relate. I'll be using this example with us. And as we go forward, I'll talk to you a little bit about what correlational designs are, and then I'll plug it into this example. So correlational designs are looking at relationships. They're not looking at causes, but just, do these two factors tend to vary together? If factor A varies or is higher, does factor B also tend to be higher? So examples, do grades in school correspond with hours of TV? You might expect that the more hours of TV you watch, the lower your grades in school are, because you're not using time to study. Do we know that's true? We don't. So we might conduct a correlational study to find out. Do years of education correspond with income? Would it be true to say, in other words, would it be true to say that higher levels of income correspond or relate to years of education? And then back to our example, does happiness correspond with blank? And some people have hypothesized money, some people have hypothesized close relationships. And we're going to examine the money one here. We're going to, at least I'm going to show you how this would be done if we were hypothesizing that income was somehow related to happiness. And what I would do if we were in class is I would ask you to write down your overall average level of happiness and your income. In other words, I might say, please rate your happiness on a scale of 1 to 10, and please tell me your average typical weekly income, okay? And so you might average it out, you'd come up with two numbers, and for each point, I would for each response, I would put a point for you on this scatter plot. Let me demonstrate that for you here by exiting out of the slides so I can pull these points around. So maybe the first person that I asked about this said their level of happiness, I can get this a little bit bigger for you, said that their level of happiness, actually, let me orient you a moment. You can see that here on the x-axis, I have these levels of income. And I just put income in hundreds of dollars, ranging from $200 to $1,000 a week. The y-axis variable happiness I have on a scale of 1 to 10. And let's say the first person said they earn $700 a week and their happiness level is 7. Then I would put their point right here above this line for the $700 and over at this line for the level of happiness. The next person said they have $200 a week, but they have 6 level of happiness. Then I would draw the point for them here. And I would keep asking that question and plotting your points. So I'm going to just move these points around as if I had asked each of you. And in the end, what I would have is sort of a pattern, a design of these points that we might be able to measure in some way. But for now, we're just going to kind of eyeball the design. So let's imagine that after I asked you that question, the points looked, whoops, let me undo that. The points looked something like I have displayed here, okay? So in this case, the factors that I'm going to point you to are in what direction are the points going? And you can see that if you tracked a line through the center of these points, kind of tried to make it as near to the most points as possible, you would have it going in an upward direction. So keep that observation in mind. And let's put a line here. We'll call this our line of best fit or our regression line. And let's put it here kind of in the middle of these points. I'm eyeballing it. That's fine. That's the way we do this for this. I'm saying, oh, I think the line of best fit, the line that's closest to the greatest number of points, would go right about there. The second thing that I would look at in this chart is how close are these points to the line? If these points were really close to the line, we'd say this is a pretty strong relationship. If they looked, whoops, if they looked something like this, and if the points were really far away from the line, we might say this is a weak relationship. And it might look something like this. Okay, so let's put this back into slideshow mode and move forward a minute. So this is our scatter plot. It's showing our income level as it relates to happiness and with imaginary data. And in this case, we probably have, given the way these points look, we probably have a moderate relationship if these points were real. So let's move on about this and look at it some more. Our scatter plot or scattergram depicts the data. The points on the plot represent individual scores. So all these points are like each person answering the questions I asked you. The axes represent the values on each scale. So here in this example, in my example, the x-axis had income. In this example, the x-axis has minutes played. So these are the number of minutes they're playing in a game of some sort. And on the y-axis, we have points scored, how many points they scored in that game. So, and the line of best fit is that line that's drawn as close to as many points as it can be. So that's the basic of looking at a scatter plot. In this case, you can see the points are very close to the line. So we would be saying this is a strong relationship. Or we might say there is a relationship between minutes played and points scored, but a word of caution, we would not say playing more minutes causes a person to score more points. And we'll talk more about this in a bit. So how can we quantify this relationship? We use a method, if the relationship is linear, meaning if the relationship has points that in general follow a single line, then we use something called a Pearson R value. We won't go into the computation. This isn't a statistics class, but I will tell you what this number means because you'll be seeing it when you look at research. So I'm going to just exit out of here again and tell you a little bit about this. The Pearson R value, it puts a number to this relationship. So we can describe this relationship with a number. And once you understand what it means, you can picture this plot without even needing to see it. So it's going to be a number, and the number is going to fall anywhere between 0 and 1. So it's going to be point something. So 0.2, 0.3, 0.4, 0.5, and so forth, all the way up to 1. And it's going to be a plus or a minus sign. Now, typically, if it's a plus sign, you might not see any sign at all. but that would imply a plus. And if it's a minus sign, you would see it. So let me just recall for a moment what I have on the next slide. Okay. I'm going to go over the next slide with you and then revisit that one. So what does the plus or minus sign mean? It indicates the direction of the plot. So if the points are generally going up, as in both of the scatter plots that we saw, we would put, it would be called positive, and we would have a plus sign. So it means the direction of the plot is upward to the right. We would also call it a positive correlation. That would be the term that you would see. There is a positive correlation or a positive relationship. It means that as one variable increases, the other variable also increases. So they're both going up. A common mistake that we see is people think of positive as good, and that's a mistake. In this case, positive only means it's going in an upward direction. So don't think about positive and negative as good and bad. So this is an example of a positive correlation. I really wish I could figure out, there we go. Let's move this up again. This is an example of a positive correlation. So the example here is ours revising your exam and exam results. You can see it's positive because the points are going in an upward direction. The line of best fit would be drawn in that direction. And you might also, and we'll get to this later, you might also say it's a fairly strong relationship because these points are pretty tight along that line of best fit. So a negative sign means that the direction of the points is going downward. It's called a negative correlation, or else you might see it written as an inverse correlation. As one variable increases, the other decreases. Don't say negative is bad. That's that same mistake again. In this case, there's no good and bad. There's just positive, negative, indicating direction. So, and I'll point out one last thing on here in a moment. So the number of flu jabs given, flu shots we might say, corresponds inversely with people who get the flu. So the more flu jabs, the lower the flu. The fewer flu jabs, the higher the flu. In both these cases, there is a classic mistake, and I'll give you a moment to see if you can observe it. Take a look at the second bullet point on both of these. And the mistake is this: revising increases success. That is implying what we would call a causal relationship, and that's a classic error in interpreting correlational results. So it could be, in fact, that revising increases success, but it could be that having success increases your motivation to revise. So once you start getting A's, you're more motivated to work harder and revise your paper. Or there could be some other factor causing both of these. Maybe you have some really good study partner, and the really good study partner both causes you to revise your paper more, and because you're studying with this person, you're getting better exam results. So we can never say causal relationships from correlations. We can never say A causes B. And the same thing right here. It's less likely that the reverse would be true in this case, but flu jabs given causes people to have less flu? Maybe. We can say maybe. But it could be that people who have gotten the flu in the past are just more likely to get a flu jab, and in that case they have less flu for that reason. Or we might say that people who are very attentive to their medical care are both more likely to get a flu shot and less likely to get the flu. So that could be another interpretation of a correlational relationship. We'll get more to that later, but I wanted to give you those examples. So what does the number in the Pearson R-value represent? Well, the number represents the strength of the relationship. The closer the points are to the line of best fit, the stronger the relationship. If the points are far from the line of best fit, the number in the R-value will be close to 0. And if they're close to the line of best fit, the R-value will be close to 1. So if the points are exactly on the line, the number would be exactly 1, and that would be called a perfect correlation. So let's go back now to that, to this slide right here where we're working on the money and the and the happiness variable. And let's pull that line of best fit into this cluster, this imaginary cluster of data that I imaginarily gathered from you. And we'll draw it, maybe that's about the closest to all the points. Then that Pearson R value is sort of like the mathematical average of the distance of each of these points from the line of best fit. So we would be measuring these distances, and the mathematical computation is more complex than that, but we would be, in essence, we'd be getting the average distance of these points to the line. And after a little bit of calculation, we would get that value between 0 and 1. So that's a little bit about the Pearson R value. You'll see that in various research, and it's super important to understand correlations because they're misinterpreted all the time. So in psychology, we have guidelines for what determines a weak, a moderate, and a strong relationship. So if the Pearson R value is 0.2, and it could be a plus sign or a minus sign, that doesn't matter. But if it's 0.2, that's a weak relationship. If it's 0.5, again, it could be a plus or a minus sign, it's moderate. And if it's 0.8, we'd consider it strong. The plus or minus sign does not matter. And you'll remember why the plus or minus sign doesn't matter. It's because all that's telling us is whether the points are going in a positive direction or a negative direction. So here are some examples using a different variable corresponding with happiness. If this was the case, if I asked you take the people you're closest to in your lives and rate your closest to them on a scale of 1 to 10, and I plotted it, then we might have closeness on this variable. It looks like this is ranging from 0 to 1.2 actually. So 1.2, you're very close. 0, you're not close. The other variable, happiness, ranging from 0 to 1. And we would see that these points are fairly close to the line, and this actual cluster is 0.85. So this would be, we would say Pearson R, we would have that little lowercase italicized R, and we'd say equals 0.85. And we'd consider this, if we were interpreting it, we would say there is a strong relationship between closeness and happiness. If we had this cluster of points, much further spread apart from this line, we would say the Pearson R value is 0.5, a moderate relationship between closest to others and happiness. Isolation and happiness. Maybe we're going to reverse this, and instead of measuring closeness, we'll measure isolation, and this might be relevant in this time of COVID-19. The first thing we would ask then is, in what direction is the line of best fit going to be? And in this case, we'd see it's going down, and we would say this is going to be a minus sign, a negative relationship. And we would ask, how close are the points to the line? And we would say maybe the R value is 0.8. We would say it's minus 0.8. There is a mistake here because this should be a lowercase r. This is just dealing with a sample. Don't worry about that. And this would be a negative correlation. And I have here actually written into the I value, to the axes, I have activity level and sadness, and this might be another example of a negative correlation. As your activity level goes up, your sadness goes down. As your activity level goes down, your sadness goes up. Again, a strong, because this is a 0.8, it's very close to 1. Negative, because we have a minus sign, correlation. And these data are just made up. Perfect correlations fall exactly on the line. Age in months and age in years. If I know how old you are in months, I know how many years you've been living. We could perfectly predict age in years from age in months, so we would give it a perfect score, which in this case is 1. We would, if we put the plus sign here for this example, but if there's no plus sign there, we assume the plus sign is there. Another example of a perfect negative correlation, the weeks completed in the semester and the weeks remaining in the semester. If I know how many weeks we've completed, I know exactly how many weeks are remaining. So again, this is a perfect correlation, and we would give it a score of -1, a perfect score. Remember, the negative sign does not mean anything about the strength, but only about the direction of the relationship. Here are some more examples. In one, you see a perfect positive correlation. This is a high or strong positive correlation with a Pearson R value of 0.8 and a low positive correlation with a Pearson R value of 0.3. Here are some parallel examples of negative correlations, and if you look carefully, you see it's almost as if they just flipped these over. And so we have the points at the same kind of closeness to the line, but reversed. And if we saw a cluster like this, we might say it's a zero correlation. If you calculated it, the score would come out to close to zero, and there would be thought to be no relationship at all. And this might be like a relationship between how many moles you have on your body and the grades you get in school. There would be just no relationship at all, very likely, and so we'd see a score very close to zero. Now, to get a little more into the reasons why we don't want to draw causal conclusions, I give you another happiness example. This is an article from online, and it says, "Happiness wards off heart disease." That's the headline. So if you read only that headline, you might think, if I can just get happy, I won't get heart disease, because they're implying a causal relationship when they use that phrase, wards off. And then if you read on the article, they even repeat that. Being happy and staying positive may help ward off heart disease. And then they tell you a little bit about the study. So what are the criticisms of this? Well, they could be right that if you can just get happy, then you're not going to get heart disease. It's possible, okay? But there are other possible things that could be going on, and we have names for those. So the big message is correlation is not causation. This is such a common mistake that you'll see in news stories that you read. That's because we could explain it in three ways. It could be what we expect. It could be that X, the factor on the X-axis, causes the factor on the Y-axis to increase. So it could be, to apply it to that example, the level of happiness, factor on the X-axis, could cause the heart to be healthier, the factor on the Y-axis. And if you want to ask further and just think about it, how could it do that? Well, maybe it could activate beneficial hormones. In this case, we would have the happiness working through a mediary, the hormones, to cause your heart to be healthier. So maybe so. Maybe if you get happier, your heart will get healthier. But we don't know for sure without further study, because the reverse might be true, or we could have a reverse cause-effect phenomenon going on. Y could lead to X. So applied to this example, having a healthy heart, factor Y, might cause people to feel happy, factor X. How could this happen? Could we explain it? Could it seem logical or plausible? We could say, sure, maybe those people with a healthy heart, they're looking around and seeing so many of their friends having unhealthy heart, and they just feel grateful for their health. So in that case, having a healthy heart causes people to feel happier. So that's a reverse, and we don't know which is true. Or it could be something totally out of the picture, some other factor that causes X and causes Y. What might this be? A third factor, which we'll designate with a question mark, and that factor might be exercise. Might both cause people to feel happier, that's the factor on the X-axis, and to have less risk of heart disease, that's the factor on the Y-axis. So in that case, there's something else going on entirely, and it's not really related. It's not that X and Y are directly related, it's that this other factor is creating what appears to be a relationship. So I'd like you to know these. We'll be applying them. So expected cause effect, that's what you're predicting. Reverse cause effect, the opposite of what you predicted. Or third variable, alternate explanation, some other factor causing X and Y. So in class, we're going to be working through some examples of these. We want to apply this quite a lot, so I hope to see you there. And if you're not able to make it to class, that's just fine, because we don't even have a class time assigned. So you watch this later, and I hope you can glean the same information. Thanks for stopping in here.